Hello, what you're going to see here today is a eval board demo video for a high side shunt current sense amplifier using one of our new products, the ISL28634 instrumentation amplifier. What you see here today in this system is you have a power supply for the shunt load that we're going to be measuring. This is a DC electronic load that will actually be pulling all of the current for the load. A DMM to measure the output of the instrumentation amplifier. The instrumentation amplifier is powered off a 5-volt power supply. The shunt load is on this board right here using an equivalent shunt of 1 milliohm. To give you a summary of what you're seeing, I have together a block diagram of the system. We have the DC power supply. I've set it to actually 1.8 volts. A DC electronic load that will be consuming all of the current. A 1 milliohm shunt resistor going into our ISL28634 instrumentation amplifier, powered at single supply 5 volts. This instrumentation amplifier is a differential output. It has a 2.5 volt input reference to center the signal with your differential outputs. Okay, so the first thing that you see right here is I'm going to be putting a very small current through this shunt resistor of 10 milliamps. And with 10 milliamps of current going through 1 milliohm, you would expect a input signal of 10 microvolts to the amplifier. Well, this is a very small signal for any analog signal processing. So if you were to go into an MCU, you would need a very high resolution A to D to be able to measure 10 microvolts. So normally you would just put this amplifier into a very high gain state. Luckily, this instrumentation amplifier does have programmable gain. It has 2 gain switches on board where I can toggle the switches to change the gain states. So if we look at the gain table of this instrumentation amplifier, I am using the ISL28634. And for a case of trying to measure 10 milliamps, which develops 10 microvolts across the input of the in amp, I'm going to want to set a very high gain setting of 1000. So with 10 microvolts input at a gain of 1000, I would expect 10 millivolts of output. So here I've set the amplifier gain already to a gain of 1000, and you can see at my output I'm measuring 13 millivolts while sensing 10 microvolts of input voltage off 10 milliamps of shunt current. Well, one could say there's an error between what's being expected and what's being actually read. Well, one thing you got to remember with any amplifier is the inherent DC VOS of the amplifier. And if you look at the data sheet for this part, you could see for the input stage, the amplifier can have up to 5 microvolts of offset. When you put this amplifier into a very high gain state at a gain of 1000, that means you can have up to plus or minus 5 millivolts of DC offset. The output stage offset can be neglected because in a instrumentation amplifier, all of the gain is present at the input stage. So any offset at the output stage is basically overwhelmed by the gain times the input VOS of the amplifier. So if I were to turn off this load current, you could see what the actual output offset is due to not having any input voltage. So turning off the load current, as expected, you could see a DC offset of 3 millivolts. So if you translate that back to the input, this would be 3 microvolts of input offset. And I said earlier that this amplifier can have up to plus or minus 5 microvolts of offset at room temperature. Okay, next let's go and put some real heavy current through this shunt resistor measurement. At the other end, I'm going to put up to 10 amps of current through this shunt, and I'm going to measure it through this 1 milliohm shunt resistor, and I'm going to develop 10 millivolts of input voltage. Since my input signal is much bigger now, I don't need such an aggressive gain, otherwise I would saturate the amplifier. So I'm going to set the gain of this amp to 100, and I'm going to expect a 1 volt output voltage. Okay, so first let's set this load generator to 10 amps of current. Okay, now you could see I'm pulling 10 amps of load current from my generator. I'm sorry, from my dynamic load, and it's going through the shunt, and it's going to, through the 1 milliohm shunt, it's going to develop 10 millivolts of input voltage. Remember that my amplifier is still at a gain of 1000. That is going to saturate the amplifier, and I want to set it at a smaller gain. In this case, I want to set it at a gain of 100. Going back to the table for the programmable gain settings, for a gain of 100, the gain setting switch states I want to put up in is in the high Z state. So I'm going to set this back into the high Z state. And as I said earlier, at 10 amps of current through 1 milliohm shunt, I'm going to develop 10 millivolts of input voltage. Putting it through a gain of 100 of the instrumentation amplifier, I would expect an output voltage of about 1 volt. And that's what you're seeing here, with 10 amps of current through the shunt of 1 milliohms, developing 10 millivolts. Putting it into a gain of 100, I'm getting 1 volt output. So this little video shows you the capability of an instrumentation amplifier being configured in a high side shunt current sense amplifier. What this application is useful in is for people who want to measure current into their low voltage FPGAs, DSPs, or ASICs, which can consume up to 10 amps or 100 amps of current on the high end, and sometimes into the tens or hundreds of milliamps at the low end. And if you want to use a very low ohmic value shunt resistor to minimize power loss in your shunt current sensing, you would need to choose an amplifier that has very low input offset and very low noise at the input. And this is what the ISL28634 that I'm using here today offers in an instrumentation amplifier, in addition to the programmable gain features, so that you don't need any external resistors to dynamically change the gain of the amplifier. On this little board here, just to finish up the video, it is, just to give you a better look at it, this is another eval board. This is for a low side shunt current sense amplifier, using just a single amplifier in a differential configuration for low side current sensing. This is not as accurate, or some people prefer to operate in the high side and some people prefer to operate in the low side. This eval board gives you the option of operating in a low side current sense using a single amp, but gain is fixed, so using your external resistors you have to fix the gain. The application note is AN1777, also available on Intersil.com. Thank you again for watching this demo video for a high side shunt current sense amplifier using the ISL28634 instrumentation amplifier.